Hi, and welcome back to Chm1032 Lab Online. I am your host, Dr. Russell Betts, and I'll be guiding you through today's experiment, which is solutions and electrolytes. Part 1. A student will observe the electrical conductance of a solution. Did you know that? If you dissolve electrolytes in solution, the solution becomes conductive. It can conduct electricity. We'll experiment with that. Part 2. A student will determine the concentration of sodium in a food product. So you're going to grab another food off your pantry or from your fridge that has a nutritional label, and we're going to do some math with that. All right. All right, part 1, determining the electrical conductance of solutions. Now, strong electrolytes, weak electrolytes conduct electricity. Strong electrolytes conduct electricity very well and will light up a lamp quite brightly because it can conduct electricity very efficiently. Now, a strong electrolyte is any molecule that dissociates in water completely, 100%, to give you ions. No parent molecule is left behind. For example, sodium chloride is a great example, actually. Solid dissolves in water to give you sodium aqueous plus chloride anion aqueous. Notice in this chemical equation, the sodium chloride is in the salt form. It's never in the aqueous form. In the aqueous form is sodium ion and chloride ion, 100% dissociation. That's a strong electrolyte, and that's going to give us a solution that's highly conductive. It can conduct electricity very well. Conversely, a weak electrolyte does not dissociate completely and will conduct electricity very poorly because it doesn't have a lot of ions. So let's take a look at that. Vinegar, acetic acid, common weak acid, plus water will give us H plus, aqueous, plus acetate ion, aqueous. And this is also aqueous. Notice here, before in sodium chloride, the material on the left-hand side was a solid, didn't dissolve in water, it just dissociates in water. Here, the parent molecule, the molecule that gives birth to the ions, actually exists in water as well. In fact, predominantly in a weak electrolyte, the non-ionized form exists predominantly. The ionized form exists only slightly. In water, in case you're wondering, is in liquid form. Okay? So this is a weak electrolyte. It does not dissociate completely in water and therefore conducts electricity very poorly. So in this experiment, if you see some solutions make this light light up brilliantly, that's a strong electrolyte. If it lights up weakly, that's a weak electrolyte, if the light is dim. And there's also non-electrolytes, which when you submerge the electrodes in water, like you do down here, nothing happens. The light doesn't turn on, not because it's unplugged or anything, but because the solution that's underneath those electrodes doesn't conduct electricity. And that's how we're going to determine whether a solution contains strong or weak electrolytes. In part 2, we'll be calculating the percent of sodium in a food product. Very simple, very fun to do, kind of cool. Now, when you're doing this, you need to get a food item from your pantry or your fridge that has a nutritional label on it. And we need to read that nutritional label and pull off the amount of grams in a serving size and the total grams in a serving size. Now, we're also going to calculate the thinking too much. 3, 2, 1. In part 2 of today's experiment, we'll be calculating the percent sodium in a food product. We'll be doing that by 3, 2, 1. In part 2 of today's experiment, we'll be looking at the sodium content of a food product. We'll be calculating the percent sodium in our food, as well as the molarity. Now, to do this, you need to grab an item off your counter or out of your pantry or your fridge that has a nutritional label and make sure your food item contains at least some sodium. If it contains 0 sodium, find something different. A bag of chips is a great example of something that contains sodium, and chips just taste good. Now, reading the nutritional label, you need to pull off the grams of sodium in a serving size, as well as the grams or the mass of a serving size. You need both of those to calculate the percent of sodium in your serving size, in your sample. To calculate now that you've seen what I expect of you, let's do an example together. We want to calculate the percent sodium in our product, and that's going to be the grams of sodium. So let's put Na because that's sodium over grams of a serving multiplied by 100. So now, if we look in here, we'll see that there's 2 different serving sizes. This is a label for a pouch of soup, or a cup of soup they call it. In one pouch, there's 12 grams of soup material, and they want us to add a cup of water to it to make the cup of soup. No problem. We're going to work with the grams though, because we want to get a mass. So grams, the serving size is 12 grams. So that's the amount of powder that's in the pouch to make the soup. So that's going to be on the bottom, 12 grams of soup stuff. Okay, the soup stuff is just whatever's in the pouch. Now, we also need to know how many grams of sodium, but we only know milligrams, right? All right, so we got to convert milligrams to grams. 360 milligrams. So you put grams up there and multiply by 100 equals. So all I did was I converted milligrams to grams. Not a big deal. You guys can all do that probably in your sleep by now. Get out your handy dandy calculator. 0.36 divided by 12 equals, multiplied by 100 equals 3%. That's that's the percentage of sodium in our food product. And that's just by reading the nutritional label. So this particular cup of soup, the pouch contains 3% sodium. And that's how you calculate the percent of sodium in a food product. But now, what if we wanted to know molarity of sodium in the finished product with the water added? Let me just clear my board here. That's the only way I know how to clear it. Now, we just calculate a percentage of sodium in the pouch. Now we're going to calculate the molarity of sodium in the complete cup of soup, in the finished product, and what we're about to drink. We're going to calculate molarity. So we know that we have, there we go, 360 milligrams, and we know that equals 0.360 grams because we just literally calculated it, right? And we know that the serving size is 1 cup, but lucky for us, the manufacturer also put the metric value with the serving size. So 1 cup equals 240 milliliters. So luckily for me, I don't have to do that calculation. The manufacturer told me. You may not be so lucky. Hopefully you are. If you're not, get a different food product. So now we need to calculate molarity, right? Molarity is moles over liters of solution. We don't have liters, we have milliliters, but that's not a problem for us, right? That's not a problem for us. We have the expertise. 240 milliliters multiplied by something to give us liters. Milliliters on the bottom, liters on the top, 1001, 0.240. Make that a little bigger. Not a problem for us. We are expert chemists. and that value will go down here. Now we need to calculate moles. Again, we are expert chemists. We know that, let me change colors, 0.360 grams multiplied by something, grams on the bottom, moles on the top, dimensional analysis, it is the best thing ever. So now, all we need to know now is the molecular mass of sodium, which I happen to know is 22.99. If you don't know it, you go to the periodic table and you look. You find sodium and you look for its molar mass. Bust out your handy dandy calculator and you take 0.36, divide that by 22.99, and you get 0.0157 moles. And that number goes up there. So now we would get 0.157 mole. Divide that by 0.240 liters. The molarity is 0.0652 moles per liter. There's your answer. Okay, that's how you calculate molarity. It's a little bit more complicated than percentage. It's just one or two more calculations. Not a big deal for you guys because you guys are experts at calculating molarity and using the dimensional analysis method for converting. All right, so now with that, I want to wish you all good luck and good chemistry. We'll see you soon.